On this note, let's thank Ray once again. Our next talk will be given by Yoshida, who's going to talk about basic science and the status of Jefferson electronic violet.
Okay, so that was actually a perfect introduction to this particular talk. So I was given this invitation to talk about EIC science in JLEIC status. And this gave me a little bit of a pause since this is a workshop about EIC science. I'm supposed to come in on the first day of this symposium and talk about EIC science. So I've decided to split this into two talks. This one is going to be EIC science. There's another one going to be JLEIC status, which will be relatively short, but I will have interesting news for you. After discussing this with Ray, we kind of decided to give a different talk on EIC science, given actually this venue and the expert audience that sits here. So we have been collaborating on a magazine article for about 6-7 months now, on and off, mostly off, but sometimes on. And actually, somebody said they were recording this. We have to check whether it's really okay with magazine publishers. So anyway.
Oh, I see.
Yeah. So as EIC becomes more and more real, we will need to talk to people beyond nuclear physics and even science. And so we thought it might be interesting to show what we have been thinking about to this particular expert audience. And so this talk is co-authored by me and Ade. I made the film, but the script was written by both of us. And the second talk is the Jefferson. Okay. So the observable universe contains 10 to the 53 kilograms of ordinary matter. And this corresponds to something about 10 to the 80 protons and neutrons at the center of atoms. So where does the mass of the protons and neutrons come from? So in 2012, the Higgs boson was discovered at IISc. There's a big celebration. The Higgs mechanism gives mass to quarks and protons are made of quarks. Of course, Higgs mechanism gives mass to other things, among other things, the quarks for this particular discussion. But it turns out that the quarks make up only about 1% of the proton mass. So where does the mass of the proton come from? So quarks and gluons and protons are bound together by an interaction called quantum chromodynamics. The energy stored in the proton due to QCD interaction is responsible for the mass of the proton. That much we know. But how exactly this happens is still a mystery. In fact, we don't understand truly how any of the characteristics of the nucleon comes about in the fundamental QCD interaction, characteristics like spin and nucleon-nucleon interaction. Now, the characteristics of the protons and neutrons, nucleons, singly and collectively nuclei in concert with electroweakland gravity forms the visible cosmos. So hydrogen helium is created in the Big Bang 15 billion years ago. At some moment, a stellar fusion takes place, an element up to ion is created, and then in this circle of nova neutron stars merger, in 14 to 5 billion years ago, are formed elements, and about 250,000 years ago, from all of this, we emerge. So all of this depends, in some way, on the characteristics of protons and neutrons and how they are. So nucleons have some mass, spin, bulk nucleon interaction. They arise out of quark and gluon interactions through quantum dynamics. So nucleons are an emergent phenomenon of QCD that we still don't really understand. Now, 50 years after the discovery of the quarks, we're finally at the threshold of beginning to unravel this mystery. And this is the story of how we got here and where we're going next in this great adventure. So, how do we see quarks and gluons? So, in the first part of the 20th century, you learned to see atoms. Before that, we knew there were atoms, but you didn't really see them. We began to see them because some people noticed that the wavelengths of the X-rays are about the same size of the distance between the atoms. And from there, you could actually figure, you could see the atoms from X-ray diffraction. This is double helix, viewed via X-ray crystallography. So in the same way, we learned to see inside protons in the 60s using powerful electron beams. So electron beams interact with protons through virtual photons, which have a wavelength, and that wavelength is about the size or smaller than the size of the proton. And this led to the first, this idea led to the first electron accelerator at SLAC. This is under construction. This is one of the really big mega projects in the physics at the time. And from this, we learned that actually protons are composed of gluons. So we have an immediate problem, however. If you look at atoms, although we have to worry about quantum mechanics in this kind of a dynamical system, atoms are located at definite position in space and mostly in the space between them. Quarks and gluons, which are a million times smaller, well, they're much, much smaller themselves, and in space in between them, a million times smaller, are deeply quantum mechanical, and they exist only in superposition and infinite number of configurations. Or, in principle, the tool that we use to probe the proton structure, so this bit and this tool that we probe the proton with, are in principle quantum mechanically entangled, and we can't tell them apart in principle. So how do we deal with this? So shortly after the discovery of the quarks, Feynman and Bjorken came up with the Parton Model. They said, well, imagine the proton is going very fast. Then because of Lorentz contraction, they become like a pancake, they're flat. And essentially, they have no spatial extent, at least in the z direction. And if you probe these things inside the proton fast enough, then they're frozen. And we can measure the fraction of the momentum that's being carried by that, or the proton being carried by that particular quark or parton. And this is a very naive way to look at it. However, this turned out to be essentially correct. So in the 60s and 70s, quantum chromodynamics developed. So this is to be compared with quantum electrodynamics, which is the interaction of charged particles, electrically charged particles and photons. The photons are the carriers of this particular force. And they couple, and the photons couple to electric charge. With QCD, a similar thing takes place. We place electrons to quarks, photons to gluons, which they carry the force. Electric charge becomes color. Now the gluons, which are the analog of photons in QCD, carry charge, and there's a couple of gluons. And this has several very profound implications. One of them is that the further apart color charged objects are, the stronger the forces are between them. Unlike the electrical charge case, where the forces get weaker as they have parts. This is shown in this particular distance. And it's very difficult to calculate anything when the coupling is very, very low. So in fact, what we learned, and this is called asymptotic freedom confinement. So essentially, if the particles are energetically interacting, they're equally bound, and they're basically, whereas we try to pull them apart, they're very, very strongly bound. So in this theoretical breakthrough, it was shown that in energy interactions, the quarks are equally bound, and QCD is a viable theory of quark interactions, and partons equals quarks is a viable hypothesis. This also implies, by the way, this quark-gluon development. So how and where can we solve QCD? So out here, when we have high energy interactions, we can actually calculate how quarks interact with gluons and how they can be probed via some charged particle. Here, the coupling is very large, and we can't actually figure those things out. These things that we actually started out asking about, we still can't do them. There is a lattice QCD sidebar in this article, probably we'll talk about this point. I'm not going to go into. So in this way, the quantum entanglement in the first instance is resolved. As long as the probe has small enough wavelength, and the probe, the virtual photons and protons are not entangled. So this bit turns out to be separable from that bit. But this means that we can measure the momentum distribution of quarks and gluons, but in one direction only. And the momentum distribution itself has its origin in the uncalculable part of density. So you gain a picture of the proton, but an imperfect one. So we measured this X distribution, and it has an extra wrinkle, which is that as you probe with higher and higher resolution, you resolve more and more quarks and gluons being emitted, so that as you go to smaller and smaller fraction, and the resolution improves, you see more and more gluons, in fact, and C particles. And this is shown here as Q squared, which is the resolution increases, function of X. This was measured, this is a measurement of error. And in fact, we see that the gluons, this is Q squared 10 GeV squared, is incredibly high as you go on in smaller index. How fast, how far can this ride go on is a question which was raised 20 years ago that we'll come back to. So what does this give us? So essentially, we've now figured out how we can measure distributions of quarks and gluons longitudinally. They're going very fast. This is exactly what happens at the LHC. So at LHC, we have particles of, we have beams of protons and protons colliding each other. And here, because of our measurement, we can actually predict the flux of the particles, the quarks and gluons as they collide. And this is a diagram that takes up a gluon from one proton and the other proton to produce 6 particles. And having measured this, you can actually predict how often such a particle is created. So this is great for the LHC, but on the other hand, as we said, we haven't really gotten very close to the initial questions of where the nucleon properties arise. So what's happened in the last 30 years is that we began to learn to turn this thing, which is a pancake from sideways, around to see it from the front. So we began to actually understand the transverse, how to measure the transverse properties of quarks and gluons. So in the old factorization, we could only look at this as a pancake. But now we can actually look to see this head on and actually measure multidimensional quantities of the partons inside the proton. So this kind of measurement has been going on for actually some time now. So there's measurements being done at Daisy Laboratory in Germany, Hermes experiment. There's current experiments being done at CERN Laboratory, experiment called Compass. And in the US, Brookhaven, I'm sorry, and Jefferson Lab.
Is it a solution to the EIC?
It's Rick's. We're going to rename one of the labs Brookhaven. Anyway, so the advances actually in recent years on all fronts actually means that we can actually move ahead in this particular science even further. So this is the origin of the US-based EIC proposal, and I'm going to go through this particular thing because the pages went through it. Okay. So EIC science will measure quarks and gluons and relate and transverse quantities, the position and the momentum, and relate this information. This is imaging. So this is really imaging the correlations of positions, momentum, spin, density, and map the relation between the parton state. So these are some of the naive calculations or models that we have at the moment. We're going to do this for you. Okay. So the other piece of it is that Terra discovered this dramatic rise in number of gluons carrying a small fraction momentum of the proton. And as this goes on, this cannot go on forever as X becomes smaller. And Parton recombination must balance the Parton split. This is called saturation. This is arguably unobserved at Terra. But with EIC, we may imagine that we will see this because we're using nuclei and gluons overlapping. In addition, in nuclei, interaction probability is enhanced by 8 to the 1/3, just from geometry. But there is another additional question: will nuclei saturate faster as color inside nucleus and nuclear interaction? So we're moving from nanometers, nanostructure, to femtometers and femtostructure. This is a much harder problem. This system is highly relativistic, highly quantum mechanical, and strongly coupled in a way that this system is. This is going to be unlike any other dynamical system yet studied. So we live in a world which is kind of amazing. My telephone recognizes my face. It's rather odd. And this would have been unimaginable 100 years ago. But 100 years ago, we learned to map atoms inside matter using X-ray crystallography. This is where it all began. Deep knowledge of atomic structure and electromagnetism is the basis of our today's technology. It's an atomic or nano science. So we're reaching the limits of nanotechnology. This is a plot of the feature size and expectation of feature size of microelectronics. So we are expecting to flatten out at about 10 nanometers, about 100 atoms wide, and the progress becomes more and more difficult. And this is why Moore's law is working. And this means that our technology is actually limited by the size of the atoms. Can we go smaller? So a nano world is here. A femto world is 1,000,000 times smaller. Can we manipulate quarks and gluons? Sounds like a crazy question, but I am not sure that this is crazier to have asked that question 100 years ago, when we just began to actually explore where atoms are in solids. So we have known for half a century that quarks and gluons have their interactions, and their interactions make up 99% of the mass of the visible universe. However, we had no way to map quarks and gluons in the nucleus. The first part. Question.
Oh. Second part.
I can go to the second. Okay, so this is a completely different talk. It's about the upgrade to the JLEIC design. As the base shows, there's a report from the National Academy of Sciences which spells out certain requirements for the electron-ion collider. So root S between 20 to 100, upgrade of 140. Ion beams from deuterium to heaviest stable nuclei, 100 to 1,000 times their luminosity. I will discuss this, what this means a little bit later. And at least 70% polarization for electrons, protons, and ions, 1 or more hour of individual acceptance. So, this is an update. So you are the first audience, I believe, who's going to hear this. So the fundamental concept is unchanged. We have a written report in 2015, which is updated to 2017, and this is this update. The document is not quite finished yet. It is under development. So the idea here is to increase the root S range by increasing ion dipole bring from 3 Tesla to 6 Tesla, keep the footprint of the design the same, the luminosity performance to satisfy the requirements that we saw before, and IR retains high acceptance, polarization remains high, with all relatively small design changes. So we will, by going from 3 Tesla to 6 Tesla, the electron range stays the same. We will increase the proton energy range from 30 to 200 GeV. And this should be upgradable to 400 GeV. We use the high energy LHC or XCC dipoles, which is being developed now. The assumption here is that the upgrade will take place quite sometime after, obviously, the construction of EIC, which would be getting on towards 2040. So this puts the Jefferson Lab EIC energy 20 to 100 GeV, upgradable to 140 GeV. Most of the design remained the same, as I said. Electron complex is unchanged. Ion complex is mainly incremental change, the biggest one being this 3 Tesla to 6 Tesla. It has pre-integrated high acceptance IR. This is being reoptimized for high energies. And at the moment, we're working with 2 IRs with the same acceptance. It has DC and cooled beam, bunch beam coolers. It also has incremental changes, but we add here a no bunch beam cooler concept. So high luminosity is achieved using multi-phase cooling. So there's 2 kinds of cooling: DC cooling and bunch beam cooling. I understand mostly theorists. So DC cooling is sort of a known technology. Bunch beam cooling is kind of still a lot of. So the DC cooling, a lot of it exists. It does push technology a little bit. The 3 MeV DC cooler, this pushes it to 6 MeV. The DC cooling is used for emittance reduction. Bunch beam cooling is really used for emittance conservation against intrabeam. The bunch beam cooling has not changed. It does push the parameters a little bit more than before. And the figure 8 is the same. So the figure 8, as you may or may not know, is there to preserve polarization. So the idea is very simple. Instability is going that way, cancels instability is going that way. You may or may not know that the person who actually invented this is the same person who invented Siberian snails. So there are several, I guess 2, 3 experts and theoretical experts in accelerator science will work on this kind of thing. And Slava Bjorken-x is the inventor of this particular. So the important thing for you is that this preserves the polarization of proton like ions, including deuterons, and electrons at greater than 80%, therefore also satisfying the requirements that we stated earlier. So now I'm going to talk a little bit about luminosity and what it means. So the NAS report said 100 to 1,000 times the Hera luminosity. What does that exactly mean? So this is Hera luminosity, delivered luminosity for days of running. This is Zeus. And you can see that it delivered about 600 inverse picobarns over 1,000 days of running. This means that Hera delivered something like 0.6 inverse picobarns per day or 4 inverse picobarns per week of integrated luminosity during the running. There were 2 collider experiments, so I'm going to inflate this to 6 inverse picobarns per week. And the real reason, of course, is that if I make it 6, everything turns out to be on numbers. So you can blame this in the Babylonian. Okay, so 6 inverse picobarns per week divided 1 week in a second is 10 to the 31 square centimeters per second. This is the average luminosity of Hera while running. So that means that if you have 10 to the 31, if you run for a week, in real world conditions, you get 6 meters. So we'd like 100 to 1,000 times Hera luminosity. So the aim is 0.6 to 6 inverse picobarns of running, or average luminosity while running with 10 to the 33 or 10 to the 34. Okay, so 6 inverse femtobarns per week is 100 inverse femtobarns per year, assuming 10 to the 7 seconds in a year. So this is a single mass here. This is 1/3 of the year. So average luminosity while running is quoted for Jacobson value. So I want to emphasize that operational inefficiency is already taken into account. I mean, you can actually take the number, efficiency, average efficiency, and multiply how long you think you're going to run and get the integrated luminosity. This is a plot. 1,000 times here, 10 to the 34 is here. 100 times here, 10 to the 33 is here. 100 inverse femtobarns per year, 10 inverse femtobarns per year. So this is the curve that you would get with both DC and bunch beam cooling. However, we can also dispense with the bunch beam cooling and still get very good luminosity. So luminosity is 100,000 times ampere over the energy. This is also so with the upgrade, the luminosity curves look like this. Of course, this is a lot more assumptions built into that curve. If you look at the amount of luminosity which is actually discussed in the white paper, divide this up into EP low, EP medium, EP high, phase 2 at 140 GeV, and deuteron or light ion, calcium, and amphibia ion. You get a table like this. See the references. If you add this up, it's something like 640 inverse femtobarns. And as we discussed before, 10 to the 34 will give you 6 inverse femtobarns a week, so 100 inverse femtobarns. 10 to the 33 will give you 10 inverse femtobarns, compared to this kind of number. So this is a summary. The basis of the design, the ring high luminosity with high repetition rate, high polarization, full event coverage, and technical risk has remained constant, I guess, since 2003, as they just pointed out, not 5. The energy reaches 20 to 100 up there to 140. Design delivers average luminosity as opposed to 10 to the 30 to 34. In the entire energy range with only DC cooling necessary. Achieves 80% polarization, greater than 80% polarization for large ions, including gluons and electrons. Pre-CDR with full description is under preparation. There may be minor changes to the parameters upon its release. The overall design risk is low. Technology demonstration is mostly needed for the bunch beam electron cooling. However, very good performance can be achieved with DC. Thank you.
Okay, questions to
I didn't catch what happens with heavy ions. With heavy ions, old.
They work fine.
Yeah, well, I didn't see it on your paper, so the luminosity.
Oh, the luminosity is essentially the same.
Is what?
It's essentially the same.
Okay.
You are 640 inverse. One slide back.
Yeah.
If you mind.
Yeah.
Yeah. Thank you. So as you know very well, of course, some of the things can be measured at the same moment. I don't have to measure gluon spin separate for TMDs with longitudinal.
Yeah, this was taken into account. So anything in the brackets can be done concurrently with the other measurements. The other ones cannot.
Okay.
Yeah,
I'm a bit surprised because I did a similar exercise and I didn't come up with this. But you took also, for example, for DVC as a 100 inverse femtobarn, which is only for some measurements.
Yeah. So
for
what
some
I did,
special spin. But okay, so you took this already into account. That wasn't so deep. Okay.
Yeah. So what I did also was to add the transverse one, which is
if you do LT, you need a
Yeah. So I doubled that.
Which of course you can always average out the L and then you get only transverse. But okay, fine, you already took something like this into account.
Transfer spin, you need a transfer spin separate.
So
this is transfer spin, I'll let you know the spin.
But sometimes it's a single spin asymmetry, you know, when you need only UP. Okay, it is already taken into account. That was my main question.
So the other thing is, I do assume that unpolarized cross sections can be reconstructed from polarized ones.
Yes, absolutely.
Which is not completely obvious. If you have to measure, you know, the uncertainty that you buy by having a polarized beam is
you have to average out your polarization very well, and you have to make cuts.
Yeah, yeah. So it's not completely obvious, but I'm assuming that can be.
Question.
Since I will be talking a little bit about the threshold region to produce epsilon,
Yes.
for discussing the mass.
Yeah.
I was just wondering whether the luminosity reach that you have at the low center mass, part that's between 20 and 40, whether there is any hope that you can actually get it a little higher.
Here.
Yeah. So that
Well, yeah, I think things do become difficult now because of the lower energy. So we do think that there is a very good chance that this will at least be here. So we think there's no real showstopper for the expansion.
There's some people talking about mitigation of space charge effects at lower energy, but then you really end up with unknown territory, so I don't think anyone really knows. A lot of people are looking at it. That's the problem. We have to find a scheme models to mitigate space charge.
Of course, doing the JLEIC threshold of these energies is very tough. The best, you know, Quarkonian to work with.
Yes.
And of course, as you know, the cross-section then drops by another factor of 10.
Yeah.
I was just wondering what is realistic in that.
Yeah, so there are multiple effects that you have to factor in. Space charge being one of them. But I think we can take a look at that. But I think there are difficult.
Like somewhere around 25, how much can we go up?
Well,
You get to 34, I know. Otherwise, you can't get enough content.
well, I mean, I think the thing is you can probably get it up, but then you have to change other things about the machine, which may not work as well in other areas. So that's the trade-off.
But is there like a special tool that you can be running that at some point just to beef up the luminosity there?
One thing you can do is change your electron energy, so you can always go to the lowest electron energy. But there also, you can in an area, how low can you go? So most of us say we don't go below 3G. There's more than 3G in play. Some level still arbitrary.
And then 3G, if you want to see those kind of leptons, as we discussed in your detectors, that is a major challenge, because simply with one detector to have the same response is kind of really tricky. So
there's ways.
Yeah.
That's the problem.
absolutely. Yes.
Yeah,
I'm thinking running with high, you know, high electron energy, meaning 10 GeV.
Well, and then the ion unit becomes interesting. So also, you know, so there are effects of not really being at the speed of light, which begins to actually affect the timing of the machine itself, which is kind of a difficulty at that end for ions.
Thank you.
Question?
Can I change to another topic already? People don't do this. I would like to go to the science piece.
Sure.
I have a question for them.
Okay. Actually, we're very happy to hear any criticism.
No, I actually want to ask something about the science piece. Is there any way how we can better fold in the use of spin? Because the problem is more or less, yeah, there's great arguments.
The use of spin.
That's correct.
Or
Is it something
something
that's, yeah, why essentially, you make a comparison with X-rays, and we look at the image,
Yeah.
you get this whole spiel of, and I think we can argue to go to the femtoscale easily.
Yeah.
I think that's a good argument to get there. I think you more or less can, because the argument to use nuclei is also relatively simple, because we want to look at nuclei at the femtoscale.
Yeah.
But then the question is still like, okay, now why do we all argue about polarized collider? So it would be nice if we have some simple examples. Why say polarization helped in the past? To follow that a little bit more in the global story.
Yeah, right. Of course, in this, in this story, in that story, polarization is obviously important. Obviously, maybe, but the fact that nucleon-nucleon interactions are a certain way and how they come together is obviously the spin as well as all the other characteristics.
So you want to flush that out more?
I think so. Good question. Like, it's true. Then you might be able to point out that to the spin part of the interaction that we have. If you wouldn't have a spin piece of any interaction, we would have or whatever, but somewhere then the spin comes in.
Yeah.
That might be useful.
I think that's a good suggestion.
And I think they would probably make a comparison to neutron scattering, right? Which is really sensitive to the magnetic properties of the material. Whereas photons are not so ideal in that respect. Whereas on the Gluon level, relativistic, there's no difference, right? So you can do both at the same time. That's a big difference.
There's this famous, there's a famous quote by Bjorken that says that spin has killed more theories.
And then
Particle
than
physics,
any other single
than any other
parameter.
period. So we have a list of those kind of experiments.
Okay, good.
Sorry, but
Just one point about this advertising the spin, since you are speaking about getting to this work level, means the manipulating to some extent, means that you have to understand orbital motion. And orbital motion, spin is the way to understand orbital motion. Maybe in that way it can enter the game, then it will be a lot more clear. Without it, it will be much harder.
No, I think these are good suggestions. We do only have 3,000 words. So.
No, but it's probably true that if you go to your atom, there you have more or less that structure and interaction are separate. That's not, so that's the way to speak.
Yeah, right. I wasn't supposed to do that. Sorry.
No, that's fine.
Push the wrong button.
Just push the same button.
Just the way to combinations between atoms. Spin is a way to measure combinations between. So,
Yeah, no, I think we can do that. Yeah.
okay.
All right. Let us thank Rick once again. We have 25 minutes to have coffee break and try to now message.